So far, we have learned several basic machine learning algorithms, linear models, decision trees, support vector machines, and artificial neural networks. There are more machine learning algorithms on the playground. So in order to get better models, we can, of course, create better machine learning algorithms. But have you ever thought about another possibility? That is trying to create better models based on the models that are created using the basic machine learning algorithms that we learned to create models that can provide better performance is possible. And that is what we are talking about today, the ensemble learning. So for today's lecture, we will first give an introduction to ensemble learning, to take a look at the basic things such as the definition, such as why it can work, when it can work, and how it works. Then we will look into the three basic categories of ensemble learning. That is bagging, boosting, and stacking. Since now we are talking about ensemble learning based on supervised learning, so the ensemble learning that we will be discussing in today's lecture were mostly about supervised learning. Recently, there are also some new studies about ensemble learning for unsupervised learning, but that will not be discussed here. So again, 4 parts for today's lecture. First, we'll take a look at the definition, why that ensemble learning can work. Second, we will look at the 3 major categories of ensemble learning one by one. For each of them, we'll first take a look at the basic idea of that type of ensemble learning. Then we'll go through the procedure for implementing that using the pseudocode. And we will cover the most popular algorithms within the 3 categories. So the idea behind ensemble learning can be described as union is strength, or many hands provide a greater strength. So you can take a look at this figure. We have several, we call it base models. They are the models created using the machine learning algorithms that we learned in the previous lectures, such as SVM, decision tree, linear models. These models can be created using one type of algorithm or can be created by different types of machine learning algorithms. But all the models then can make their own predictions, and the predictions can be combined in some way to create a ensemble method. And that ensemble method can generate a strong model. And that is the idea of ensemble learning. And those base models, sometimes they can also be called weak models because they provide relatively poor performance. Then the target model, the ensemble learn, that model that we're trying to create, so which is called the strong model because it can provide better performance. And the common algorithms that we use to create base models includes what we learned before: linear models, the support vector machines, decision tree, the k nearest neighbors, which we haven't learned yet, and the artificial neural network. And the most common one is the CART decision tree. Which is what we learned in the lecture for decision trees. That's the most common one. And depending on whether the base models are created using one algorithm or using different algorithms, we have homogeneous ensemble learning or heterogeneous ensemble learning. For ensemble learning, there are 2 key steps. One step is that because we need to create different base models, that means we need to have different data. For example, you're trying to use this one algorithm to create different models. That means we need to have different data. But we know that we are dealing with one problem. We only have one data set, one training set. In order to get different data sets to create different base models, we need to involve sampling. Sampling means that we want to get data samples from that one data set for everything to create subsets that we will need to use for creating the base models. And that process is called sampling. For sampling, there's a few typical sampling methods, and the three that we will be dealing with, there are bootstrap, We will talk more about the definition of it. The other one is adjusted sampling. The other one is the total population sampling. The other key step is called a combination. Once we get different base models, and each base model can give us one prediction for one sample, then we have multiple different predictions. But we know that the ensemble, as the combination of all the models, can only give out one overall prediction for the whole ensemble. In order to get that one overall prediction, we need to find out a way to combine the predictions made by different base models. And that process is called a combination. For combination, if we are talking about a regression problem, usually we use algebraic combiners. For example, we can use the mean, the sum, the weighted sum, the product, the maximum, the median of the predictions made by different base models as the final prediction or the overall prediction. And if we are addressing a classification problem, then we can use voting-based methods. We can use the majority voting. That means the winner needed to receive over 50% of the votes. And we can also use plurality voting. That means the winner will receive votes that are greater than the others. And there's one third category in this combination step that's called stacking. That's also one major category of ensemble learning methods. So stacking, the unique thing about stacking is that it used one machine learning model to serve as the combiner. So instead of using a rule, for example, use the mean, use the majority vote, then what we use is just a machine learning algorithm to tell us, what is the final prediction based on all the predictions made by the base models. Then let's take a look at a few key questions for understanding ensemble learning. The first two questions that we want to understand is whether ensemble learning can make better predictions and when that can happen. So we can take a look at one example that is shown in this figure. We have three different conditions. In all of them, we can see that we have three base models, model 1 to model 3, and they are used to make predictions for three samples, sample 1 to sample 3. So let's take a look at the case left. And you can see that model 1 this is a binary classification problem, either negative or positive. So you can see that for model 1, you make a prediction of negative for sample 1 and a positive for sample 2 and positive for sample 3. For model 2, it's very similar, positive for sample 1, negative for sample 2, and a positive for sample 3. So now we want to create an ensemble as a combination of the three base models to make an overall prediction. And if in this case, let's say that if we want to use a voting-based method based on the plurality, so you can see that for sample 1, we have one negative that is predicted by model 1 and two positives predicted by model 2 and model 3. So based on the plurality rule, the overall prediction should be positive. For sample 2, we should have do it in the same way. So we will also, because we have two positive predictions and one negative predictions, so the overall or the final prediction should be positive. For sample 3, the prediction made by the ensemble should also be positive. And in this case, if the two labels of the three samples are positive, you can see that the ensemble make perfect predictions, right? The accuracy is 100%. And that is better than the accuracy that can be achieved by any of the base models. And you can see that in this case, ensemble actually improves the performance of all the models, right? That's the condition 1. Then let's take a look at the second case. We have very similar thing with three base models and we have three samples, but now the predictions made by the different base models are a little bit different. And for all the three models, you can see that the label should be negative for sample 1 for all the three models and positive for sample 2 and sample 3 for all the three models. And then if we use the ensemble based on a plurality voting based combination rule, we can see that we should also get the predictions of negative for sample 1 and the 2 positives for sample 2 and sample 3. And if we take a look at the two labels, it is identical. It is negative for sample 1 and positive for sample 2 and sample 3. In this case, you can see that the prediction by the ensemble is identical to the predictions made by all the 3 samples. There's no change, there's no improvements, there's no adverse effects. So that means the ensemble takes no effect in this condition. And then take a look at the third one on the right. So for the 3 samples, we also have the predictions made by the 3 models. And in this case, we use the same plurality combination rule. The ensemble will make a prediction of negative and negative and negative. And in this case, if the 2 labels are positive, positive, and positive for the 3 samples, you can see that all the predictions made by the ensemble is wrong, right? And if you take a look at the performance of base models, each of them actually they made one correct prediction. The other 2 are wrong. For example, model 1, the prediction for sample 3 is correct. And in model 2, the prediction for sample 1 is correct. And then for model 3, the prediction for sample 2 is correct. So each of them, they have accuracy of 33%. But the ensemble, the accuracy is 0%. So in these conditions, you can see that actually the ensemble reduces the performance. And then we get back to the 2 questions that we are interested. First, whether ensemble learning can improve the performance of the base models. The answer is yes, it is possible, right? At least in case 1 on the left, we succeeded. Then the second question, if that's possible, when that will happen? And this one actually gives us some hints. If we try more examples like this, we will find that the ensemble can improve the performance of the base models under specific conditions. That these specific conditions are that the base models need to be first good enough. If they're really bad, you combine them, it's possible that you will make something that's even worse. So that's one condition. Second condition is that the base models need to be different. So that's just like case 2. You can see that if all the models, they will give us the same predictions, then it will make no sense to combine these models, right? Because it's for sure we will not make any improvements. Next, let's see how it happens. Let's use a more specific example. For this one, we are trying to do a binary classification problem. We have points represented by positive signs and negative signs. There are 2 types of points. So for the same, we have the same data point, but it's possible that we can create the different models. In model 1, we're trying to separate the positive signs from the negative signs. And one way of doing the separation is like what we had in base model 1. We are trying to separate the 4 positive signs on the left part of this domain from all the other points on the right part of the domain. And that will give us model 1. And that boundary between the blue region and the red region is served as the boundary between the 2 categories. Then in base model 2, we try to focus more on the negative signs. In this case, we separate the 4 negative points from all the other points on the left so that we can get a different classification results. And then for model 3, we observe that there's more positive points in the upper part of this domain. So we can draw a horizontal line to separate the positive points from negative points. But you can see that for all of the 3 models, they make some good predictions and they also make some incorrect predictions. For example, in base model 1, 2 positive points, they fall into the region belonging to the negative points. So the predictions for these 2 points will be wrong. And then 1 intuitive way of doing this ensemble learning, of course, is to combine the results from the three models, right? It's possible that we can get something like what we had in the lower part of the figure. You can see that we combine the lines, three lines for separating the two categories in the three base models. It's possible that we can get a new boundary for separating the two types of points. And that's what we're trying to do in ensemble learning. That is how to combine these base models to create something that can help us make better predictions. Finally, let's take a look at why it works, why it not works, and when we should stop. And to better understand this why question, we need to first learn about two new parameters. One is called bias. Bias is a parameter that we use to describe the differences between the prediction and the true label. So it's more like how far our prediction is from the exact solution. The second one is variance. Variance measures the differences between the different models. Let's say that we have the same data set and we want to train different models based on the same data set. Then we get different models. And these different models can give us different predictions. If we compare the results of these different models, we can get variance. If we have a high variance, that means that these different models, the results predicted by these different models will be much different from each other. So to better understand the definitions of these two parameters, let's take a look at the figure on the left side. So for this figure, actually we have two axes. The horizontal one is bias. So left means lower bias, right means higher bias. And for the y or the vertical x, we have variance. And lower means we have lower variance, and we go higher, that means we have higher variance. So we combine four different conditions: low bias, highest, low variance, and high variance. We will have four different conditions, just like what we have here. And which one do you think is the best or is the most desirable one? Think about it. Without any understanding of ensemble learning, I think most of us possibly will give a guess that is the lower left one is the one that we like the most, right? We want to have the condition that all the predictions that are very close to the center of this target. That's what we want. And this one actually corresponds to the condition in which we have lower bias and a lower variance. Lower bias, that means all the points are close to the center of the target. And a lower variance, that means all the points, they are close to each other, so they cluster together. And then we go to the left upper one. You can see that the center of all the predictions actually are not far from the center of the target. That means that the bias is not high. So we have low bias. However, because all the points, they are scattered everywhere, they're far from each other, that means we have high variance. And if we go to the right upper one, that's kind of the worst one, because first, the center, the average of all the predictions, they're far from the center of the target. So that means we have high bias, and all the points, they are far from each other. That means we have high variance. And the one in the lower right part, that one, you can see that all the points, they are close to each other. That means we have low variance. However, the center, the mean of these predictions are far from the center of the target. That means we have high bias. So four different conditions, and we know that the high bias, high variance is the worst condition, and low bias and low variance, that is the best condition. And the other two, both of them, they have their own problems, but they also show good performance in one aspect, but not two of them. You can see that these two parameters, bias and variance, are what we can use to describe the performance of a group of machine learning models. That in this case, we're talking about ensemble learning as a group of machine learning models. So we can also use these two parameters to gauge the performance of an ensemble as a combination of some basic machine learning models. In order to tell or to better understand why we can get better machine learning models or how to do that, we need to take a look at the relationship between the performance of an ensemble or a group of machine learning models and some other key parameters. The key one is the model complexity. If we take a look at this figure on the right, it shows the performance, a general trend between the model performance, which are characterized by the two things, bias and variance, and the level of complexity of machine learning models. When we have very simple models that we have very low model complexity, because they're very simple, usually they cannot give out very good predictions. So most of the models that we create using simple models that we created use the algorithm, they will give us pretty bad predictions. So the bias will be pretty high. And as we improve the model complexity, they can be better. They can be used to make predictions in a better and a better way. So the bias will be reduced in that process as we increase the model complexity. And in the other aspect for variance, when we have very simple models, they may only predict a few things. So the predictions made by simple models may not be too different from each other. That means the variance will be low. But when we have more and more complicated models, they can be used to consider more and more specific conditions. So the predictions that we can make with these complicated models will be much different from each other. That means the variance will get higher and higher as we increase the model complexity. So you can see that the variation of the bias and that of the variance, they exhibit totally different trend with the change of the complexity. One, the bias will decrease and the variance will increase. So the best model or the optimal model will be obtained at the point when the two curves intersect with each other. But in reality, actually, it's difficult to get something like this. We just use this figure to show us how to get the best ensemble model. And it's from this figure, at least, if we take a look at the complexity, we can see that it's possible. There's one specific point existing there. And then later, when we are talking about different categories of ensemble learning, we will also see that some categories of ensemble learning methods, they may be good at improving the bias, while the others, they may focus on the change of variance. The classification of ensemble learning methods is pretty clear. There are three major categories of ensemble learning algorithms. They are bagging, boosting, and stacking. We understand these three major categories of ensemble learning algorithms from the perspectives of democracy. So for bagging, it works in the way that we are trying to create different ensemble learnings and then try to combine the predictions based on make an overall prediction based on prediction made by the different base models using rules such as voting or averaging. So this is kind of the pluralist democracy. So we're trying to take advantage of the opinions made by the majority of the base models. And for boosting, the idea stems from the elitism. That is, we are trying to create better models and then try to give better models more weights in the final voting process. So this one is the elitist democracy. And the third one, stacking, it utilizes the idea of hierarchy, that we are trying to create another level of models and use that model to manage the base models. So the base models, they can make their own predictions. Then the second level model trying to use the predictions made by the first level of models, then to make the final prediction. First, for bagging, And the procedure as what is shown in this figure. We have the original training sets, we have the unlabeled samples, bar X bar, and we have the labels represented by a vector Y. Then we used that bootstrap sampling method. So here bootstrap is a very representative sampling method. The idea is that we first, for example, we have 100 samples and we are trying to collect 30 samples from that pool of 100 samples. So we get 100. We draw all the samples out based on a distribution. For example, uniform distribution. That means for each sample that we want to take out, the possibility is one sample over the total number of samples. In this case, 100. And for the second one, when we are trying to do the second sample, we throw the first sample that we just draw from that original pool, we throw it back. Then we want to collect one sample from that original 100 samples again. So we do it for 30 samples to get the first subset. And that's the first sampling process. We generate the first subset. Then when we are trying to generate the second subset, we do it in the same way. So we throw all the samples back into the original pool. Then we always have 100 samples when we are trying to collect one sample out for the second sample set. So this type of sampling process is called bootstrap sampling. And you can see that we have the original sampling set and we want to create, in this case, capital letter T subsets. And for each subset, we have unlabeled samples and also their corresponding labels. And we use each subset to train one separate sample. For example, subset 1 is used to create or to train model 1, and subset 2 is used to train model 2. So eventually, we will get capital letter T models or base models in this case. And these T base models can make T different predictions. Next step that we do in this procedure of bagging is that we will combine all the T predictions made by the T base models. And we use one specific type of combination rule. Then we can get the final prediction as the prediction made by the whole ensemble. So this is for the training process. For the testing process, we will have a separate testing set. We just need to feed the testing set into all the base models. So their T base models, they will also make T predictions. And then we let the T predictions to go through that combination process. We will get one prediction for the testing set. And here, this is the pseudo code for implementing basic bagging. So you can see that the input that we will need for bagging is that we will need to have a training set. Here, X1, Y1, that is the unlabeled sample and the label for sample 1. Then X2, Y2 for sample 2. Here we have M samples. Then we also need to have the algorithms that we use to learn the basic models. Here we call it L. That's the algorithm. It can be one algorithm. For example, it can be a supported vector machine, or it can be a combination of basic machine learning algorithms, depending whether we are talking about homogeneous ensemble learning or heterogeneous ensemble learning. We also need to define the number of base models. In this case, we use capital letter T to represent it. Next, we need to do the initialization. We need to initialize all the base models. Here, H small letter t means the base model T within all the base models. And the combination of all the base models will give us the capital letter H. That's the ensemble model that we are trying to get. We can use, for example, in this case here, we just give it a placeholder, and later on we will update this H. Next, we will need to use iterations with T, capital letter T steps. So for each step, we will need to first use the bootstrap sampling to create a subset. D1, D2, DT. So for any subset D sub a small letter t, we can create a base model H sub small letter t based on the algorithms that we use to get the base models. Here's L. And after we go through all the t steps in this in the iterations, we will get capital letter T base models, and the combination of all these models will give us the capital letter H. So that's the ensemble model. And finally we get the capital letter H. We can use it to make predictions for any testing data. So the pseudocode that we just showed actually is for basic bagging. It's very similar to there's no fancy stuff. You just follow the basic procedure for bagging. There's another one which is also very famous. It's a bagging algorithm called random forest. So from the name, you can see that it's related to what we learned before about the decision trees. Here we have a forest. That means we have multiple trees. And there's another keyword, random. So the key thing for understanding this random forest is to understand where does the random come from. So let's take a look at the pseudocode for it. The input is very similar. We have the training data set and we have the algorithms for base learning models. But in this case, since we are talking about random forest, so we need to use decision trees as the basic learning algorithms. We also need to define the number of base models, capital letter T, as the input. The first step, we need to initiate all the base models. Next, we also need to have the iterations to create the capital letter T base models. So first, we also need to use a bootstrap sampling process to get one new subset for each iteration. Next, we need to train a new base model for each new subset using a modified decision tree algorithm. Here we need to modify it because we need to add in the keyword random. Here random means that in the original decision tree algorithm, for each node at which we want to split the data set, usually we need to select a feature based on which we can split the data, right? Because each feature or each attribute had different attribute values, and that based on what attribute values for different samples, we can split the data at this node into different subsets. And in original decision tree algorithm, we want to select one feature from all the available features. But here we want to add some randomness to the decision tree algorithm. What we do is that instead of using all the available features, we just want to use a small subset of all the available features. For example, if currently we have 10 available features to select from, then we want to create a subset only with, for example, 5 features, and we will only select one feature from this subset of 5 features as the feature that based on which we want to split the data. And then we select one feature from that subset, and we split data and create a decision tree based on it. So in this way, we have T capital letter T iterations. We can create T capital letter T decision trees. And finally, we combine all the trees and with the additional randomness that we add in by slightly modifying the way that we select the feature for data splitting at each node, we will create capital letter T base models, and then combine them as the final ensemble model. And use the ensemble model, we can make predictions for new samples. That's the idea of random forest. The second major category of ensemble learning, boosting. So the procedure is like this. You can see that we also have one training set as the beginning, but now the sampling process is different. So we do it in a sequential way instead of in a parallel way, just like what we did in bagging. In bagging, bootstrap sampling, so each sampling process is independent from the other one. It will not be affected by the previous sampling processes. But when we come to the boosting, the one sampling process will be affected by the previous sampling processes. It happens in this way. So when you take a look at the first sampling process, we have capital letter X bar, we have vector Y. We do the first sampling process so we can get X, capital letter X1 and Y1 as the unlabeled samples and labels. And it's a subset of it, and then based on this subset 1, we do the training, we can get base model 1. So for model 1 and the sampling process for X1, Y1 and the training of model 1, because there's no sampling process before it, so it will not depend on other sampling process. But when we get to the second sampling process for creating X2, Y2, now this sampling process will need to depend on the previous sampling process. In sampling, in the first sampling process and the training with the data obtained by this sampling process, we will find that model 1 will make good predictions for some samples and if possible show bad performance on some other samples. So for this case, we will mark those samples, who have good predictions and the samples who have bad predictions. Then we will give those samples that are incorrectly predicted higher weights in the next sampling process. So that is more likely that these incorrectly predicted samples will be more likely selected in the next sampling process. In this way, the new samples, the samples that we want to train with the data set created by the second sampling process, they will have more samples that are incorrectly predicted in the first sampling and training process. So X2, Y2 will have more samples that are incorrectly predicted in the first sampling process. So in this way, you can see that the sampling process for the second sampling process depends on the first sampling process and the training process. So we do it in this sequential way. We go to the last one. Let's say that's the capital letter teeth sampling process. So the possibility of drawing different samples from the training set will depend on the results that we got in T-1 training process. If there are some samples they are not correctly predicted, then it's more likely that they will be selected in the sampling process, the last sampling process, T, capital letter T. And actually there are two different types of weights. The first one is the weight of the samples. That means for every sampling process, different samples, they have different weights. So we combine these different sample weights, we will get a distribution, right? And for example, some samples have a higher probability of being selected. That means they have a higher sample weights. So this is the first type of weight. The second type of weight is associated with the model weight. So in different sampling and training process, for example, sampling and training process for model 1, we can get the performance of model 1. If model 1 has a very bad performance, then in the later combination process, we want to make sure that this model have a lower weight in the combination. And for example, for sample 2, it shows pretty good accuracy, exhibits good performance. Then we want to make sure that it has a greater weight in the final combination process. So in this sequential sampling and training process, we will assign different sample weights and different model weights. And in this way, we can get better and better models and let these elite models to have better and better weights, which can be used to better combine the different models. For the testing process, it's very similar. We have a separate testing set, and we will feed the testing set to all the models. And in this case, the different models will give out different predictions, and different models, they have their own weights, which are determined by the training process. So they get different predictions. Then we combine the predictions based on the model weights. And here's a more specific example to show the idea of boosting. So you can see that we actually went through this example before, but now we're trying to look at it from a boosting perspective. So here we have two categories of points represented by the positive signs and negative signs. First, we're trying to draw a vertical line to separate the two types of points. On the left, we say that is for the positive points, and on the right is for the negative points. But you can see that the first base model actually made two false predictions for two positive points on the right. So here, these 2 points will need to be given higher sample weights in the next consideration, right? So next, in order to do this, what we do is that we want to move that vertical separation line to right so that these two incorrectly predicted points can be correctly predicted in the second base model. And actually, that's what we did. So in the second base model, you can see that now for the two positive signs, which we made incorrect predictions, now because we moved the vertical separation line to right, now they can be correctly classified. However, in the second model, we still find that there's another problem. That is, we have 3 negative points that are incorrectly predicted. So we need to give these 3 points a higher sample weights so that in the next model, model 3, they can be correctly predicted. In this case, what we did is that we draw a horizontal line so that these 3 models can be correctly predicted. But if we keep continuing this process, we will see that in model 3, we still have 2 positive signs and 1 negative signs that are incorrectly predicted. So we keep doing this process. And for each of the 3 base models, each of them, they can have their own model weights, for example, based on their accuracy. For example, model 1 made 2 errors, and model 2 made 3 errors, and model 3 made 2 errors. So the number of errors can be correlated with their model weights. And then based on the weights, we can combine the 3 models, and eventually we can get the one on the right. That's the ensemble as the combination of all the base models. So this is the idea of boosting explain it using a specific example. For boosting, we have 2 very popular boosting algorithms. The first one is called Adaboost. The procedure is stated in this pseudo code. You can see that the input, we also need to have the training data set, different samples. We also need to have the algorithms that we can use to learn the base models. Here we call it L. We also need to define the model of base models. Here we use the capital letter T. First, we want to initialize the sample distribution. Here you can see this letter D is actually not the data set, it's the distribution. So D1 is the possibility distribution that we use to draw sample for the first sampling and training process. And you can see that here we use a uniform distribution. Let's say that we want to draw I samples out of the original training set. So you can see that here we have I samples, but each time we want to draw I samples out. Actually, this is in reality, usually we want to draw just a subset of samples from the original training set. So it shouldn't be I. Originally it should be M, here should be I, and I should be smaller than M. So there's a typo here. Then we also needed to use a iterative process with T iterations. And for each iteration, we need to train a base model based on the samples that we obtained from that sampling process. So here you can see that we have the D here means the data set that we get actually should be D sub 1. And this another D sub T, this is the distribution that we use to generate that subset. And with these 2 things, we can get a base model for iteration T. Next, for this iteration, we can also calculate the error that we get. We call it epsilon T. And here is for a binary classification problem. So HT, that's the current sub-base model. If it equals to the true label F, then in that case it's correct. If it's not correct, that means there's error, right? We add all the errors up, we will get the overall error. That's what we want. So for binary classification problem, if the error here is greater than 0.5, then we jump out. If it's smaller than that, we will get alpha t. So that is what we use to calculate this model weight. So you can see that how significant a model would be in the combination. That's the model weight will be determined by the error made by that model. So if one base model have a very low level of error, in that case, it should have a higher rate. But on the contrary, if it has very high error, then it should have a low weight in the final combination. And also the distribution for drawing the samples in the next training process will also need to be modified. Here in the current iteration T, so we need to talk about the distribution for drawing the samples in the next training set. That's T plus 1. Is related to the distribution that we used in the current sampling process via this equation. And this equation also have this alpha t in it. And we know that alpha t also is relevant to the error. So we get two new types of weights. We get the weight for drawing the models, and we also get the weights for drawing the samples, and also the weights for the models. And by going through the capital T iterations, we will get capital T base models. Then we combine all the base models. Now we don't combine them directly. We know that different models have different weights alpha t. So alpha t times ht will be the contribution of base model T to the ensemble. And we add all of them up, we will get the ensemble model. Here we have a sign function because this is for a binary classification. If it is, for example, a regression problem, then we just need to get the weighted summation of the predictions from different models as the prediction of the final ensemble model. Another very popular boosting algorithm is called gradient boosting. And this one may be a little bit more difficult to understand. We need to understand it this way. Here we want to draw an analogy because you can see that in the name we have something called a gradient. So can you guys still remember when we learned gradient before? That is when we are talking about the deep learning, right? The artificial neural network. We are talking about a gradient descent. So for gradient descent is the optimization method. When we want to, here is the same thing. We also want to obtain the model that will give us the optimal performance. So we are trying to look for the optimal model. In that way, we can also use the gradient descent algorithm. But now it will be a little bit different. It's like this. So first, let's take a look at the first equation. This capital letter H represents the ensemble, right? That's the combination of all the base models. And that one is actually can be obtained using the base models using this equation in boosting. So HT, that is the number T base model, and alpha T, that is the model weight of that number T base model. So we get a weighted sum of all the base models, we will get the ensemble or the ensemble model. So that's actually what the equation that we used in gradient boosting. And next, we want to take advantage of gradient descent. So we take a look at the equation that we used before for gradient descent. We want to update something, for example, the weight W, then the weight W for the new step equals the weight W for the current step minus alpha, that's the learning rate, and the partial L, partial W, that's the partial derivative of the loss function with respect to W, that is the parameter that we want to update. And then we can do one more thing. That is, we also, now in this boosting algorithm, we want to keep updating the ensemble model so that it can become better and better. So we have the ensemble model for T step. can be obtained based on the ensemble model, capital letter H, for t minus 1 step plus alpha t times ht. And if we compare this equation with that gradient descent equation, we can now rewrite this equation as the equation right below that equation. That is the capital letter H, capital HT equals the ensemble model in the previous step. That's the capital letter H, t minus 1 minus rho t. Here's also the alpha thing, is also learning rate, times the derivative of the loss function with respect to the parameter that we want to update. That's h. So here h, we use the gradient at the step t minus 1. So that will be partial L, partial capital letter H, t minus 1. And if we compare this equation with the equation above it, we can see that the new base model at step t, that's the small letter ht, need to be approximately equal to this minus gradient, right? So we want to understand this graphically. We can take a look at the figure on the left. So at the very beginning, we have a guess. That blue point, that's a guess for the ensemble model. Then we want to improve it. Then what we can do is that we want to improve the model based on the loss function, and we try to make one step. The next step, we need to determine, to make one step, we need to determine two things. One is the direction, right? And we know that the direction for the fastest decrease in the loss will be the negative of the gradient. So we get the direction. Next, we want to determine the learning rate, alpha, or here the rho. So for that one, we can use one method called line search. The idea of line search is very easy. If you know the direction to go, then you just make different steps with different step size, and you go different distances, and you will find that at a specific distance, we will get the maximum decrease in the loss function. And in that way, we get the best learning rate. So learning rate is about the distance to make for this one step, and we know the direction, we know the distance, so we know where the next point will be. The next point, the distance between the current point and next point, that will be what we need to change to the ensemble. That is ht. So for the first step, then the distance from point 1 and point 2, that will be h1. And for the second step will be h2. So now, but there's one difference. That is for any of those base models, depending on what type of algorithms that we want to use. For example, we want to use linear models. Then we know what a change that we want to make in the loss function and in the prediction. So we will can find the best linear model can help us achieve the results. And for each one, we will get a different linear model. So we get one initial guess for the ensemble. Then step 1, we get the base model 1. We add it to the initial ensemble model. We can update it. And for the first step, second step, we're doing it in the same way. So eventually, the ensemble model that are updated by these different base models will help us reach the optimum performance. And here is the pseudocode for the gradient boosting. So again, the input will be very similar. We have training set. We also have the algorithm for learning the base models. And we also need to define how many base models we will have. Next is to obtain the initial ensemble. So that can be obtained using the basic learning algorithm. Next, we need to have, depending on the capital letter T value, we need to have capital letter T iterations. And for each step, first we want to calculate the gradient, that is as the derivative of the loss function with the current ensemble model. We can do it here. I showed two equations. One actually is for all the samples. The other one, we put an I here. That means we treat one sample at one time, but they're the same thing. Next, we get this gradient. We want to propose a base model that can use to approximate that gradient. So we use the optimization problem on the right. So you can see that we want to obtain the parameters that we used to define the base model. Here we call it WT, and it is used to represent the parameters that we used to define the base model HT. Just like for linear models, there are the weights of the linear models, and linear models are obtained using a optimization process as this. We're trying to minimize the difference between the difference and the predictions made by this base model HT. Next step, we get the direction. Next step, we need to know what learning rate we need to use. So we use that line search method that I just mentioned. Again, we know the direction, so we just travel different distances, and with the specific distance, we know that we will get the highest decrease in the loss function, and that distance represents the learning rate. Then with the learning rate and also the base model, we can use this equation to update the ensemble model. And eventually, after we go through all the capital T steps, we can get the final ensemble model. That is capital letter H sub capital letter T. And the input of this model, of course, is the original data set, is the X bar. Then it's the third major category of ensemble learning algorithms, stacking. So this one is much different from the previous two categories of ensemble learning algorithms. We also have a training set, but then what we do is that usually we use the total population sampling. That means that the submodels that we get will have the same number of samples as the original test training set. And usually we need to make sure that these models are, for example, they can be created using different algorithms, so that even they use the same data set, they can still give us different predictions. And the different predictions here, they're represented using Y1, Y2 to Y sub capital letter T. That is output. And we will have a second level machine learning models for the combination. We call this meta model or meta classifier if we are dealing with the classification problem. And the training data that we use to train this meta model or the second level machine learning model, the unlabeled samples consist of the predictions made by the base models. So the Y1, Y2, YT, they are combined together as the unlabeled samples. And the labels come from the label of the original training set. So we have the unlabeled samples and the labels. We combine them. We can use them to train the meta model. We train the meta model, we can get the predictions. So this is for the training process. And for the testing process, we let the unlabeled samples X bar 0 to go to all the base models, and that will also give us the predictions made by these base models Y1, Y2, YT, and they will work as the unlabeled samples for the second level machine learning model or the meta model. And then the labels in the training set Y0 will work as the labels for the meta model. So we can use this to do the prediction. Actually, the prediction can be compared with the labels to see the performance of this ensemble. And here's the pseudocode for stacking. The input, again, we have M samples, YXY, Y1, all the way to XM, YM. Then we also have the algorithms for learning the base models and the number of base models, capital letter T. First step is to initialize the base models. Then we need to go through capital letter T iterations. And for each one, we generate a bootstrap sample set from D or DT. As said, it depends. If we use the total population sampling, that means we used for all the samples, we use the same training sets, so we don't do any sampling. Then we want to make sure that we have different algorithms. But if we have the same algorithm, we can also use the bootstrap sampling techniques, so we can get different subsets. Then we use the same algorithm, we can still get different sub-base models. And next, we want to train each base model, so we will get their predictions. Next, we get the predictions from the base models. We will use the predictions and the labels from the corresponding label from the original training set as labels. So we have labeled data and training set. We will train the meta model. Here we call it H2. And the H2 again is trained with the data set D prime and 1. D prime was created using the predictions made by the base models. And after we go through all the iterations, we can make the final prediction for any testing data or any other unknown data using the H, which is represented by all the base models, and H2, that's the second level meta model. So this is what we need to know about ensemble learning. Again, it's very straightforward. We just combine models with the predictions-based models, but there are different strategies based on plurality, based on elitism, based on hierarchical prediction process. So that will give us 3 different categories of ensemble learning algorithms.
I think I'm falling for you.